Hello, everybody, and welcome to week 4. We have been having fun. I have. I hope you have too. This week, we are going to talk about resource allocation. So, starting on page 21 of the book, the importance of deterministic operations it shares in business and industry, and among other places, is due to the enormous number of real world applications that can be modeled as mathematical programs, and in particular as linear programs, integer programs, or the network-based linear programs that we have been discussing. So first, what is a resource, right? A resource is an economic or productive factor that's required to accomplish an activity, such as, something going on in your enterprise or to achieve a desired outcome, like on a project. So this includes land, capital, labor, and much more. Energy is a resource. Sometimes that's 45% of a business's expenditure. Entrepreneurship, right, costs money, right? Creating a clear vision to use these resources and then doing value stream mapping, where we continually try to reduce costs without reducing scope. What about information, right? What about data and protecting it as a resource? It's the largest resource in most companies anymore. What about expertise? Did you know that lost intellectual property costs over $600 billion a year in productivity, it's estimated? Management costs money and time. Time waits for no one, right? And so this is important to us. So a common linear programming model involves the allocation of these scarce resources to optimize some function. And in these models, the main issue is how to distribute resources among competing demands. Okay, so the book takes us then through the Terre Haute Door Company, or THDC as it calls it, right? And the thing about THDC is, as it builds doors, these are standard doors on the left, maximum or high security doors, and maximum security doors. And as it builds those, it notes that each door requires a different amount of machine labor and machine time and labor, right? And each one actually has a different profit margin along the way. So what they do in this problem is they lay this out in a chart on page 22 for us, right? The only thing I like to do, and I like to add things so that it's simpler, right, is that really consider that the same people that work on machine 1 also work on machine 2. So in my mind, I add the plus sign to that because at some point I'm going to have to consider that in some of the constraints that I anticipate. So according to this chart, each door must go through both machine 1 and machine 2, and that was a constraint that they share before it can be sold. Now, each worker is assigned to work on only one of the doors. So a worker is going to work on a standard door or a high security door or a maximum security door, right? Which means they do work on both machines, right? In addition, management has decided not to sell more maximum security doors than in order to keep the demand for the high security doors and standard doors up. Okay, so also THDC has said that it has available only 120 hours per week, with another constraint on machine 1 and 100 hours on machine 2, right? And of course 280 hours of manpower available for the entire week. So if we assume that we can sell every door that we make, how many of each door should be produced each week in order to maximize profits? So we want to define the objective function, right? We want to define the decision variables, the constraints that were in the problem that I read, but it's on page 22, your book too, to determine how many of each door, as I said, should be produced each week in order to maximize profits. So, so what we do is we break it down into the decision variables first. So typically, to begin the formulation of our model, we define the variables, right? Since our decisions are, the book says the decisions are the number of doors produced in each type. And they go ahead and define variables as x1, x2, and x3. To me, I like to keep it simple. I need to know my number of doors X of standard, doors X of high security, and doors X of maximum security. That's the way I like to write it. So these are your decision variables, right? So I've defined these decision variables as XS, XHS, and XMS, as you see there. And these represent the decision variables to be that of the doors that we're going to make, right? And once I have my decision variables, I can go ahead and formulate the objective function, right? And because I know I want to maximize profit, so profit should equal $35 for X, 40 XS, $45 for XHS, and $65 for XMS. I want the maximum of that value. And that's really what we're going for in our decision variables. So now I've defined my decision variables and I've defined my objective function that I'm looking for. Next, we're going to look then at constraints. And constraints help us understand our limitations on resources, right? So the first question I like to just surmise is, well, before I even look at the problem, is how many constraints do I anticipate, right? I could have guessed 3 or 4 based on what I've read already, and I know that in this objective function to maximize, I'm going to have a constraint that keeps everything greater than 0. So I start out with that in A. X of doors made, I can't have profit if I don't make any doors. So XS, XHS, and XMS all must be greater than 0. And so the next set of constraints is about the hours. We can determine the number of hours used by machine 1 and machine 2. So for machine 1, notice I need, from the chart on slide 3 or in your book, I need 3.5 hours to work on the standard door standard door. I need 6 hours to work on the high security door and 8 hours. And all of those hours have to be on machine 1 less than 120 hours. So I end up with this inequality. I do the same for the next constraint, which is machine 2, which requires 4 hours on for the standard doors, 5 for the high security, and 6 hours on that machine for the maximum. So I end up, and I have a constraint of less than 100 hours. Okay. So the amount of now I want to turn to the amount of labor, right? And so which was the next constraint. And so the amount of labor is calculated first for each machine and then added together, right? So each machine, one machine has labor of 5 hours, the other machine has a labor of 6 hours. The high security machine has 8 and 7 respectively, and the maximum security door machine, the maximum security door will require 11 hours on one machine and 9 hours on the other. So because they're all the same variables, I can add them together. I end up with 11x plus 15x HS plus 20x sub ms. And that has to be less than 120 hours of labor, as these workers use both machines, right? A worker will use the standard machine or the work on standard doors, or work on high security doors, or work on maximum security doors, but they will work on both machines, which is why we combined them. And then I did want to note too that we want to restrict the maximum number of security doors sold. Remember, the point there was to make sure that the demand stays high for the other ones also. So we want to restrict the number of maximum security doors to no more than that of the combined standard and high security doors. So we have this constraint here. X sub maximum security is less than X substandard plus doors plus X sub high security doors, right? So we really see 5 constraints that we will be graphing here. And so my objective function summarizes is this, or my model, actually, I should say, my LP model has an objective function now, which is to maximize this 35XS plus 45 plus 65 MS. Now, that's about profit, so which we used, we're going to maximize profit by defining with the defined variables, such that machine 1, and we did that formula, that was constraint A, and machine 2 in hours has this formula for constraint B. Constraint C we already determined, which was the labor hours, is much be less than 280 total. It was constraint C. Constraint D was that my maximum security doors has to be less than my combined standard or high security doors. And then I have actually a constraint E. This is a common constraint every time. It's a constraint, they call it, of non-negativity, right? That both X S doors, X high security doors, and X maximum security doors must be greater than 0, right? And here's one final constraint, is the solution should be only integers, right? As we solve this, we might end up with fractions or decimals, but we know that in this type of problem, I can't make part of a door, right? So in the end, we would graph our solution, which we really haven't been doing yet. We've been working on, and a computer would normally do this for you, hence part of the conversation we had about doing it manually versus doing it in a computerized fashion. But notice in the solution we're looking to find the objective function, which is how to maximize profit of these points. And so what's going to happen is we will graph the constraints or an inequality, or which we can call inequalities, right? Those are constraints, less than or equal to, or greater than equal to. That's an inequality. So we graph those constraints. So first, when we graph, we're going to find the corner points, which you see highlighted in red. And that helps us create our feasibility region. That's the shaded area in the graph. And so we have these multiple points because, remember, we're solving a system, and that helps us find the corner points. Then we want to test the corner points from our objective function by using zeros and ones or some random numbers that will help us solve it and plot it to test the corner points of our objective function. And those are going to help us find the maximum, or if we wanted to, the minimum, the maximum in this case, right? So corner points are where the maximum or minimum are going to occur, right? And so this feasibility region satisfies all the constraints. That's true, but remember so any answer in that feasibility region will work. But remember, in this problem, we were looking to maximize profit, right? And so when graphing, we want to pay attention to the intercepts that we graph in the constraint inequalities. And we want to fill in data points, as I mentioned, for the constraints with test points. No such as, that was my own note. Okay, that I didn't want to continue. So and then in the end, we want to answer the question, in this case, profit, in a sentence, right? We use a sentence to answer the question, right? And so overall, we want to figure out how many standard doors